In this lecture, we are going to first review what limits are and then start a little bit of the L'Hopital's rule. L'Hopital's rule. So a quick review of the limits. Well, here I list a bunch of definitions of limits where the limit itself could be a number or infinity. Also looking at how x behaves. X could approach a single number, could approach a number from one side, or approaches infinity. Okay, but essentially these definitions are very similar. Let's start with the most basic one. We say the limit of f of x as x approaches a equals L if we can take the values f of x arbitrarily close to L by restricting x to be sufficiently close to a, but not equal to a. What it says is when your x gets really, really close to a, the value of f of x gets really close to a number L. How close the number of f of x you want to be close to L, so you can get f of x really close to L. So if you want to say, I want f of x to be 0.1 in 0.1 range of L, then you just need to push your x that close to A. Okay, so no matter how close you want 0.0001, then you just push your x to close to A enough somehow. Okay, so that's the definition. You can get there as long as your x is close enough. You can get wherever close you want to L, but not on L. There will always be a little difference room. Similarly, when the limit is infinity, you can make f of x as large as you want, say above 2 million. Then you just need to push your x close enough to A. Same thing. 5 million, you push your x close enough to A, maybe with another number, but the difference. Then sometimes we talk about single side limit, left side limit or right side limit, where we let x approaches A from the negative side. So this is A, and your x only goes this way. So your x is like here and gets closer and closer and closer and closer to A. But you don't have the right side. Okay. And finally, we can also make x approaches infinity. And that is, you set if x, when we say the limit of f of x is L as x approaches infinity, that means, again, you want your f of x very close to L, you just push your x to be large enough. Okay, those are like the definitions in more like algebraic way. I didn't really list all of them. Similarly, you can also define negative infinity as a limit. You can also define the limit from the right side. You can also do the combination. Also, pretty much on the side of x can approach A, or A from the left side, A from the right side, or go to infinity. That's your f of x. And meanwhile, that's your x side, the x value. And then the y value, which is f of x, could same thing go to a number, could go to infinity. Oh, by the way, you can also go to negative infinity or negative infinity. So you can do all these combinations. You get 5 times 3, 15 combinations. But essentially it's the same. You get, if you want f of x to be that close to L or that large, you just push your x to close enough to A maybe on only the side that you have, or large enough or small enough. Okay, that's like the analytic definition or algebraic definition. Now let's look at how it means on graph. On graph, it means, when you make your x value really close to the number, x goes that way. As x approaches the number, how is the y behave? You follow the graph of the function. Starting from the first limit, as x approaches 0 from the negative side. So when your x approaches 0 from negative side, you follow the graph. Actually, you are going here. You approaches 0 from the negative side, and you are looking at the y coordinate. Okay, so you trace the curve. The y coordinate goes closer and closer to that open circle, which will be, this is 1, so that's 1/2. Let me take this away before I write down my number. So this is 1/2. Now the next next question, as x approaches 0 from the positive side, what is the limit of f of x? As x approaches 0 from the positive side, which on the graph is going this way, that's the graph you're tracing, not the best color. So the y coordinate goes toward the black point, which is 4. Let me just use teal. And that means when your x approaches 0 from the left side, the y value goes toward 1/2. But when your x approaches 0 from the right side or from the positive side, the y goes toward 4. They're not matching. When your left side limit and right side limit are not the same, you don't have a limit. You do not have a limit. In that case, we say the limit does not exist. Let me write it here. Does not exist. Okay. You need the left side and right side limit match. Okay, second number, -2. So when x approaches -2 from the negative side, on x it's this way, on graph it's this way, the y coordinate just go down, which is approaches -infinity. And when your x approaches negative from the positive side, the curve behaves this way. So actually you are tracing the curve that way, and the y coordinate goes all the way to the up. That would be +infinity. Same thing, the left side and the right side are not the same, so the limit does not exist. Now the third point we are looking at is 4. So at 4, when x approaches 4 from the negative side, the curve goes all the way up. So, which means y approaches +infinity. By the way, you don't have to write plus for +infinity. You can just write infinity itself. As x approaches 4 from the from the positive side, f of x goes this way. Same thing, infinity. That looks a little bit strange. I'll put the plus back. So they match each other. So as x approaches 4, the limit of f of x is infinity. So as x approaches 4, your curve go all the way up. But notice when x equals 4, actually it's not infinity. So you have like a breaking, and the curve breaks, and you have a point here. Doesn't matter. The limit is still infinity, although f of 4 is not infinity, of course. It's a number. Now, I'm not going to do single-sided anymore. As x approaches 2, which means from left and from right, the graph goes here, and they meet at this open circle, which is again 1/2. for y. Next, as x approaches positive infinity, your curve goes this way. It's not very clear, but I hope you can imagine that's 0. So it's like the asymptote. The curve will be flat and gets closer and closer to x-axis. So that's y coordinate is 0. Similarly, as x approaches to negative infinity, the curve goes this way. The y coordinate, guys, the height gets higher and higher, but not across 0 x-axis, which is 0. So this is another 0. Okay, so these are like a review of how you can understand the limit and also how the limits behave on the graph. Well, now you can try practice 1. So a function f is continuous at a number a if the limit of f of x as x approaches a is f of a. What it says is pretty much, let's use 2 as the example, that's the best. We have a limit, x at 2. When x approaches to f of x equals 1/2, so f of 2. That means if you want it to be continuous, f of 2 will have to be 1/2. If you want it continuous, which means you have to, why can't I do it? I'm trying to shade this point. It's so hard for me to do it. Okay, so you have to shade in that point so that, you see how you glue the two curves together to make the curve continuous without that missing point. Yeah, that makes the function or the graph of the function continuous. Okay, so of course our function f is not continuous at several points. Okay, our f is not continuous at x equals -2. Let me write it here. F is not continuous. The graph of f, this graph of f, okay? At the first point that it breaks, see this is one piece, okay, until this is one piece, it stopped and it started over. So that's where it stopped, x equals -2. Then the next time it stops, it was here, then it jumped to there, x equals 0. And then this is a continuous piece until you are missing the point, x equals 2. And then you keep going. Oh, it stopped. Then it starts over again. So that's the last 4. Okay, our function is not continuous at these 2 points, but it is continuous everywhere else. In general, the functions that we know are pretty much all continuous on their domains, because when we sketch them, they are like nice pieces of curves, right? Which are their domains. So pretty much here I listed the functions that you know. They're all continuous in their domains. Okay, polynomials, rational functions, root functions, trigonometric functions, exponential functions, log functions, hyperbolic functions. So for example, say 1/x. It's not continuous, it's 2 pieces. It's not continuous at x equals 0, but the domain is x can't be 0, denominator can't be 0, okay? So yes, the function is not continuous at 0 because it's not defined at 0. And anywhere in the domain, the function is continuous. And then also, not only the function themselves, the functions and the compositions of these functions. So pretty much as long as it's defined, you can do the composition, you get a continuous piece, a continuous function in its domain. that will be very important for us, because when we look for the limits, like in this example, we can simply just say, okay, x squared minus 2x minus 4 is a continuous function. 3 is in the domain. So when I have this, it will just be the limit plugged in. Okay, because x squared minus 2x minus 4 is a continuous function, you just plug in 9 minus 4. So this is negative. Oh, sorry, it's a 2. Here, 2 times 3 minus 4. So it's 9 minus 6 minus 4. That would give me negative 1. Okay, on the other hand, when we have the limit of x approaches negative 1, as x approaches negative 1, the limit of x plus 3 over x plus 1. Well, actually, when you look at the function x plus 3 over x plus 1, which is a rational function, the denominator x plus 1 tells you the domain is x not equal to negative 1. So the a here is not in the domain, which means we can't just say the limit is the function evaluated at that number. If you really do it, what you will have, it will be, I don't want to say equal, but if you plug it in, it will be negative 1 plus 3 over negative 1 plus 1. Remember, negative 1 is not in the domain, so it won't work out. You will have 2 over 0, which, well, in general, we can simply say does not exist as a number, but we could have positive and negative infinity as limits, right? So you can't do that. If you really look at what happens when x approaches negative 1, let me show you. From the positive side of x plus 3, x plus 1, it will be the limit of the top over the limit on the bottom, negative 1 plus x plus 1. When x approaches negative 1 from like higher side, this is 4. X, sorry, not 4, negative 1 plus 3, so 2. When x gets closer and closer to negative 1, a little bit higher, but negative 1, x gets to negative 1. So negative 1 plus 3 is just 2. Okay, so let me write 2 because I don't have room. But on the bottom, when x approaches negative 1 from the positive side, x is higher than negative 1 a little bit, which means x plus 1 is a little bit higher than 0. It is a 0, but it's a positive number. Okay, so when you take this ratio, it's really 2 over a very small positive number. It will go to positive infinity. But on the other hand, you can do the same argument when the limit of x plus 3 over x plus 1 as x approaches negative 1 from the negative side, it will still be the limit on the top, the numerator, over the limit of the denominator if they exist. So as x approaches to negative 1, when you add 3, it approaches 2 from the negative side, but still it's a 2. But on the bottom, it's negative 1 from negative side, which means it's a little bit lower than negative 1. X is a little bit lower than negative 1. Adding a 1, x plus 1 will be a little bit lower than 0. So this is like a negative 0 or 0 negative. I don't know how to express it. It's very close to 0, but a negative number. So when you divide 2 by a very, very small negative number, you get a huge negative number. So actually, you are going to have positive infinity on one side and negative infinity on the other, which makes the function, well, the limit does not exist. And in general, the graph, of this will be like x equals negative 1. What's the other one? X equals 1. And then you will have something like this. Oops. I don't want them to meet each other. This is x equals -1. Okay, that's like the graph where your approach is -1. From negative side, you go down to -infinity, but when your approach is -1 from positive side, you go up to positive infinity. That's how you can see it from the graph. Keep going. Third example, the limit of e to the 2x minus cosine x as x approaches 0. So this is a function composed with exponential function composed with 2x polynomial and subtracting cosine, which is trigonometry. But all these functions are defined everywhere. So all you need to do is to say, okay, plug in 0. E to 2 times 0 minus cosine 0. Cosine 0, you are here and you are looking at the x coordinate, so that's 1. We have e to the 0 minus 1 or e to -1. Okay, next question. The limit of tangent of e to the x as x approaches -infinity. Well, you can't really plug in -infinity as a number, but you can still plugging in the idea of limits. The first function that your x will be applied to will be e to the x. And the graph of e to the x looks like this. Y equals e to the x. So as x approaches -infinity, e to the x approaches 0. As x approaches -infinity, e to the x approaches 0. So this will be 0. Equals the limit as x approaches -infinity, tan of 0. And tan of 0, again, we're here, the same point, but this time tangent is y over x. So 0 over 1, which is 0. Tangent is a continuous function at 0. And anyway, you don't have x anymore, so you just plug in the number. Tangent of 0 is 0. Okay, next example, the limit of x squared minus 2 over x plus 1 as x approaches infinity. If you do plug in infinity, infinity squared minus 2 is infinity. Infinity plus 1 is infinity. The numerator and denominator are both infinity. So you can't really do the quotient. When you are having a quotient of two polynomials, to find its limit, you divide by the highest power on the denominator. That's always the case. So we divide by the highest power of x on the denominator so that the denominator will be 1. And whatever numerator turn out to be, will be what it is. So here x approaches infinity, we are having x over x, 1 plus 1 over x. On the numerator, you have x squared minus divided by x. That's x. Well, do you understand what I mean? Let me write it out. So I'm having x squared over x minus 2 over x over x plus 1 over x. That's what I mean by divided by x. I think that's clearer. So the numerator turned out to be x minus 2 over x. Denominator turned out to be 1 plus 1 over x. And as x approaches 0, this is 0, this is 0. So you end up with x over 1, infinity over 1. So that's infinity. The limit will be infinity. Question 6. I have the limit of x squared minus 9 over x minus 3 as x approaches 3. So if I plug in, well, first of all, I hope you notice it's not in the domain. And if you really plug in, you will have 9 minus 9 over 3 minus 3, so 0 over 0, which means it doesn't work. But if you factor the numerator and the denominator, well, you don't need to factor denominator, and cancel the denominator, it will just be the other factor, x plus 3. Now you can do direct plug in, 3 plus 3, which is 6. So for question 5 and 6, you need to use some basic algebraic tricks to find the limits. Okay, now you can try practice number 2 and number 3, but meanwhile, let me tell you this remark. Actually, the limit in question 6 that we just did is called an indeterminate form of 0 over 0. It's called indeterminate form is because if you just do the plugging in and sort of see the quotient, you end up with 0 over 0. Okay, because when you have the situation of 0 over 0, it could turn out to be any number as a limit. Okay, it could be any number as a limit. For example, when I say, that makes 0 over 0 a 5, then you do the limit, x approaches, what do I want to do? Infinity. That's easy, 5x over x. Oh, sorry, I wanted 0 over 0, then let me make it 0. 5x over x. When you plug in 0 over 0, but actually that's a 5, right? So similarly, if I want any number, I just do that number times x over x. But on the other hand, I can make it 0. If I want 0, x over x squared. Is that? No, the other way around. X squared over x, that would be 0. And x over x squared would be, well, I would need a positive side or negative side to make it, positive infinity or negative infinity. But you get my idea. You can make a form 0 over 0. When you have a form 0 over 0, it really could be anything. Infinity, 0, positive infinity, negative infinity, 0, or any real number. Everything is possible. So the thing is, you can't determine what it will turn out to be. That's why it's called indeterminate form. And these are the list of indeterminate forms that we have. First of all, when you have quotient 0 over 0 and infinity over infinity, doesn't matter positive or negative infinities, they could be anything. Very importantly, infinity, say positive infinity over positive infinity, they do not cancel each other. That's not right. Again, as x approaches infinity, this could be x over x squared, could be x squared over x, could be 2x over x. They could be anything. You can cancel an x, but you can't cancel an infinity because when you write them, they are all a single infinity, right? X squared is also an infinity. So that's why infinity over infinity is an indeterminate form. Similarly, when you do 0 times infinity, it's like a super small number times super big number. It could be the bigger number is really, really big that, multiplying by small numbers still will remain large. Or the other way around, the small number is really, really small. Then the multiplication will kill the larger part and it goes to 0. Or if they balance out, it turns out to be any number. Similar reason, subtraction, you are subtracting a very large number from a very large number. Then it could be anything, depending on how large both of them are and also how it is relatively. Then we are having the powers. The indeterminate forms of powers will be 0 to the 0th power. Anything to the 0th power is 1. if the base is not 0, but any 0 to any power is 0. So 0 over 0 to the 0's power, that's why it's not defined at the first place. But also, when you have this, which way are you going? Are you going with anything to 0's power is 1, or are you going 0 to anything is 0? So, can you feel it? So 0 to 0, it again depends on whether the base is stronger or the exponent is stronger to guide it to where it is. Of course, similarly, when you have infinity to 0's power, the infinity wants the power to be like so large, but meanwhile 0's power will pull it back to 1. So when you have both of them together, where it is, you don't know. And finally, 1 to infinity, you have a number really close to 1. 1 times anything is itself, but when you do it infinity times, it might not be itself anymore. Okay, so it might end up with higher than 1, even infinity. Do I want to give you examples to show you why each of them is true? I don't want to. Maybe I'll do 1. 1 to infinity. I think that is like the most confusing one. 1 to infinity. The thing is, you could really have a sequence that goes to 1. That will be x over x plus 1. Wow, that's a little bit too complicated to show. Let me think if I have a better idea. Okay. I need 1. So I'm not going to take x as a real number. I'll take it as a whole number. You will have the idea. I can't really make up something right away. When your n goes to infinity, nth root of 2 will goes to 1, because you're asking what number to the 10th power equals to what number times to 20th power equals to. The number will get closer and closer to 1. But meanwhile, you have nth power. As n approaches infinity, this is a 1 to infinity case. Okay, now here I listed something in several questions. I want you to decide whether they are indeterminate or not. If it's not indeterminate, you can determine what it is. Then you tell me the value. The first one, infinity plus infinity. A very large number plus another very large number. You still get a very large number. So that's still infinity. Now 1 to the 0's power. If your limit, the basis approaches 1 and the power approaches 0, so 1 to anything is 1, anything to 0 is 1. Both of them are pulling you to 1 instead of two different numbers, so it just be 1. Finally, 1 over negative infinity, 1 over a very large negative number, 1 over infinity gives you 0, and this will be 0, but a small negative number. So the limit will be 0. Okay, so all these are not indeterminate because you know what it turned out to be. Okay, you can try practice 4 through 6. Finally, we will introduce the L'Hopital's rule. This is called L'Hopital's. At least that's how I was taught. Suppose f and g are differentiable and the derivative of g at x is not 0 on an open interval. So the derivative can't be 0 on an open interval. Contains a. Except possibly at a. We are talking about what happens near a. at 8 doesn't matter. This is a limit definition. It's not like a continuous kind of definition. If the limit of f over g as x approaches a is an indeterminate form of quotient, 0 over 0 or infinity over infinity, then very importantly, the limit of this quotient is the same as the limit of the derivative, the quotient of the derivatives. Okay, and not only that, if after you take derivative top and bottom separately, this is not a quotient rule. Okay, you take the derivative of the numerator, you take the derivative of the denominator, then you put them back in the quotient. If on the derivative of the, if the quotient of the derivatives has a limit, then the original quotient has a limit, and this limit covers not only a real number but also infinity or negative infinity, or does not, if you know why it doesn't exist. So this is also true for the cases when x approaches other than a from one side, or approaches positive infinity or negative infinity. Okay, so if you remember example for number 1, number 2, we just did it up there in the previous example, well, not previous, but the previous calculation, question 5 and 6. Now let's do it again with the nice L'Hopital's rule. First of all, remember it only works with indeterminate form. So before you start doing the differentiating, you need to know, yes, I'm having a 0 over 0, or I'm having an infinity over infinity, because that is the reason you can do the L'Hopital's rule. Otherwise, you can't. All right. So when x approaches infinity, x squared minus 2 goes to infinity, x plus 1 goes to infinity. We do have an infinity over infinity. Then the limit will become the derivative of the numerator. Okay, so differentiate it, you get 2x, and the derivative of the denominator will differentiate the denominator, you get 1. So actually, you are just getting the limit of 2x as x approaches infinity, and of course that's infinity. On the other hand, the limit of x squared minus 9 over x minus 3 as x approaches 3, this is 9 minus 9, 0 over 0, 3 minus 3, 0. So we do have a 0 over 0. That's why we can do the L'Hopital's rule and say differentiate the numerator, I get 2x, differentiate the denominator, I'm still having the 1. So this time I'm also having the 2x, and that will give me 3 plugging in 6. Same answer, but much easier. You don't need to do all the division here, or all the all the divisions here. Remember, we divided x top and bottom, or the factoring here. Okay, now you can finish the packet with practice number 7 and 8.